Welcome back to my channel, and I can bet that I have not posted a video in last 2 months or so, maybe barely in the last 2 months. Once a video I might have posted, but I have not been so active lately, and I'm going to start from today to post at least one or two video a month. um, Today I will be talking about row reduced form of the matrix of a matrix in general, row reduced echelon form of a matrix. uh, I hope that you know what a row reduced echelon form of matrix is. It's a mouthful to say, but for the sake of this video I will just paste a picture of it from Wikipedia or something like that on the screen for you to judge how much you know and how much you don't know about the row echelon form. Row reduced echelon form. Okay, that much is the time that I can give. So let's start. So I have a general matrix V given by its rows v1, v2, v3 dot till vn, and I row reduce it to some matrix, just for example say 1 0 0 0 till the end, 0 1 0 0 0 0 0 till the end. And here surprisingly I have a dependent column, uh, which is x, y, and 0 0 0 0 till the end, and dot till n columns are completed. um, on going from v to this uh, I, no, not I, R maybe. uh, we have done few operations, few permutation and uh, row elimination operations, and I can denote it by matrices. This is a general thing, like you can do it like this. So suppose that I did some operation in sequence as E1, E2, something, 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 EJ, and that comes out to be R. Okay. So what that means, and also another fact of this uh, E kind of matrices is that it does one operation in one step. Like I have chosen it to be like that, and it is simple to see the thing that I'm going to so by assuming that they do a single operation each time they multiply themselves with the matrix. And also they are, like, you can also prove that they are invertible. And so I can write V as Ej inverse, Ej minus 1 inverse, dot till E1 inverse R. Okay. Now, if I see this column and this column, what I get is, I'm also assuming this as E. So E times the column 1 of R is equal to column 1 of our initial matrix, because there is a one-to-one correspondence with matrix of R and matrix of V. Similarly, I can write E column 2 of R to be equal to column 2 of our initial matrix. Now comes the dependent column. I can write E into C3R to be E times x 0 0 till the end plus E times 0 y 0 0 0 till the end, which is nothing but x. E times E is a matrix, x is just a scalar, and C1R plus E times y C to R. Now this is something to think about. Like, this definitely proves that the column 3 of our initial matrix, which is V3, so V3 is equal to x times V1 plus y times V2. Now, this is actually true in general. In general, every dependent column that you get in a matrix after you row reduce it, by dependent I mean the one that don't have any pivot in them, where pivot just means the leading one in the row reduced echelon form. So every column that don't have such a pivot, you can write that column as a unique combination of independent column vectors before that come before that dependent no pivot column. This argument kind of works in mathematical inductive ways. For example, if you have a matrix with columns v1, v2, vn, the first column is obviously linearly independent, because in our way of argument we don't have any other vector to compare it with. So the first vector is always linearly independent, and the second vector can be linearly independent or dependent. It can be dependent if it is a linear combination of only this vector, which means it is a multiple of this vector in some way. And if v2 is some multiple of v1, then it will get to the same form that v1 gets to if we do the same row operations on v1 and v2 respectively, which means that after forming the row reduced echelon form of the matrix, if you get 1 0 0 0 0 0 in the first column, you will get x 0 0 0 0 0 in the second column, where x is the factor by which v1 is multiplied to get v2. Now this argument goes for every other vector to which specific column vector that come henceforth. Therefore, the column vectors that don't have any pivot in them actually mean that they can be written as linear combinations of the independent vectors before that, just like this. Here v3 is the dependent vector and it depends on v1 and v2. By depends I mean it can be written in some combination of v1 and v2. It is in the column space of the matrix generated by v1 and v2 alone. It is in the span of v1 and v2. That is one half of the proof. The other half of the proof is why do x and y need to be independent? Now it kind of seems obvious, because we know that v1 is independent with respect to no one, so it is like absolutely independent because we don't compare it with anything else. And if you get something like this, it also means that v2 is linearly independent to v1. So if v1 and v2 are linearly independent and they generate some vector v3 by some combination of them, then we can be sure that it is the only combination that leads to this. Because for example, suppose that you can generate v3 with a different combination of v1 and v2, then you can subtract these two equations and get 0 is equal to x minus x dash v1 plus y minus y dash v2, where x minus x dash and y minus y dash need to be independently 0, otherwise v1 and v2 won't be linearly independent with respect to each other. So yeah, that was the proof, and this shows how you can uniquely generate columns that come, that the dependent columns that come after few independent columns, uniquely by combination of by unique combination of independent vectors that come before the dependent vector. Thanks.